Okay, hi guys. So we'll be continuing on seeing the calculation of rate constants in case of reactions which are reversible. So let's say we had a reaction which is AG converting into BG. So for forward direction we have KF as the rate constant, and for backward direction we have KB as the rate constant. So KF is the rate constant of forward direction, rate constant of forward direction, and KB is rate constant of backward direction. Okay, so let's say the initial concentration of Ag was 0 and 0 here. Concentration at equilibrium, rather concentration at time t first, was, let's say, A minus x and x here, and concentration at equilibrium finally was A minus xe and xe here. Okay, so we can write that rate of reaction would be minus d of A minus x upon dt, which is rate of disappearance, divided by the stoichiometric coefficient, which is 1, which should be equals to dx by dt, or the rate of appearance of A, or rather B, divided by its stoichiometric coefficient. Okay, and at equilibrium, what can we say? At equilibrium we can say that dx by dt would be equals to 0. This implies, so rather not implies, this is 0 because of this condition, which is rate of reaction in forward direction would be equals to rate of reaction in backward direction. Okay, so we can write that rate of reaction is equals to rate of reaction in forward direction minus rate of reaction in backward direction, okay, which is nothing but kf times A minus kb times B. So we can write that dx by dt would be equals to rate of reaction, which is nothing but kf times concentration of A minus x, concentration of A would be A minus x minus kb times x. Okay, so this is one equation, and we already know that kf upon kb would be equals to concentration of B at equilibrium this is nothing but equilibrium constant divided by rate or concentration of A at equilibrium. So we already know this fact as well. From our past set of video lectures on physical chemistry. So from these two, what can we write is so kf times, rather k, from second equation we can have that kf upon kb would be equals to xe upon A minus xe. Okay, so just simplifying it, so we will be getting kf times A minus xe would be equals to kb times xe. So from here we can write that kf times A would be equals to kf plus kb times xe. So from here we can write that kf plus kb would be equal to kf times a divided by xe. Okay, let's mark it as a third result. Okay, so from equation 1 and 2 we can write that, from here we can write that dx by dt was equals to kf times a minus x minus kb times x so this would be kf times a minus, this is from first equation, minus kb times x. From here you can calculate the value of kb from third equation, so just substitute the value of kb here into this second equation. So we would be getting that dx by dt would be equals to kf times a minus x minus, what is the value of kb here? The value of kb would be kf times a upon xe minus kf times x. Okay, so this would be nothing but dx by dt would be equals to kf times a minus x minus kf times a minus xe upon xe, just simplifying this term, times x. Okay, so from these two terms as well we can take out the kf as the common factor. So kf times a minus x minus a minus xe divided by xe times x. Okay, so just simplifying this equation, so you would be getting kf times, this would be, rather just taking the whole denominator as xe, so a times xe minus x times xe minus ax plus x times xe divided by xe. Xe and xe get cancelled out, so we would be getting dx by dt as kf times, now from these two a can be taken as a common factor and xe is also a denominator for this bracket, so we would be getting, this would be xe minus x. Okay, so now what we can see is from equation 3 was kf a upon xe, we are also getting this term kf a upon xe, this was also kf a upon xe, so kf a upon xe would be, can be written as kf plus kb. So for this, from equation number 3 we can put the value of kf a upon xe as, so from equation 3 kf a upon xe can be written as kf plus kb, xe minus x would be equal to dx by dt. Okay, so now taking the term, shifting the terms to LHS and dt to RHS and then integrating, so we would be getting that minus ln xe minus x would be equals to kf plus kb times t plus c. Okay, and when, just to get the value of c, when t equals to 0, x would be equals to 0 as no a would have been dissociated into b, so we can get the value of c as minus ln xe. Okay, so just shifting the terms here, so we would be getting minus ln xe minus x would be equals to kf plus kb times t minus ln xe. So kf plus kb times t can be written as ln xe upon Xe minus x. Okay, so in other terms we can write kf plus kb would be equals to 1 upon t ln xe upon xe minus x. So please remember this is a very important result. Okay, and if we see the graph of ln xe minus x with respect to time t, it would be a downward facing graph, downslope, the graph having downslope or negative slope. So with this we come to the end of this lecture. Before ending, just I'll write a note that whenever in examination a question says that you have been provided this data after very long time, then you will consider that they are giving you the equilibrium data. Okay, as far as the reversible reactions are considered. So data provided in the question after data which is provided after very long time. So you have been given that this is the data which has been captured experimentally after very long time of when the reaction took place, or after very long time from the initiation of the reaction, then that data should be considered equilibrium data. Okay, so with this we come to the end of this lecture. We will see a series and parallel reactions or first order kinetics in the next lecture. Till then, good luck and goodbye.